Okay, good morning, everyone. So let us now continue our lesson on Kirchhoff's laws. This time, let's now have the mesh current. So for today's video presentation, this is all about the mesh currents and then the nodes. So a simplification of Kirchhoff's law is a method that makes use of mesh or loop currents. A mesh is any closed path of a circuit. It does not matter whether the path contains a voltage source. In solving a circuit with mesh currents, again, mesh is a loop. Mesh currents, we must first decide which path will be the meshes. Then we assign a mesh current to each mesh. For convenience, mesh currents are usually assigned in a clockwise direction. This direction is arbitrary, but the clockwise direction is usually assumed. Kirchhoff's voltage law is then applied about the path of each mesh. If you can still recall what is KVL or the Kirchhoff's voltage law, that is voltage applied minus the voltage drops is equal to 0. Okay, so the resulting equations determine the unknown mesh currents. From these currents, the current or voltage of any resistor can be found. So this is an example of a mesh. It is a closed loop, a closed circuit. So in this figure, you will see there are two meshes. Circuit marked mesh 1. This part is mesh 1. Mesh 1 is A, B, C, D. So this is the mesh 1. And then mesh 2 is this A, D, E, F. So all voltage sources and resistances are known. So as you can see now in the figure, so a procedure for finding mesh currents, I sub 1 and I sub 2 is as follows. So let's see. Step 1. After the meshes are selected, so we already have the meshes. Again, we have the mesh 1, we have the mesh 2. Mesh 1 is A, B, C, D. Mesh 2 is A, D, E, F. So after the meshes are selected, show the direction of mesh currents. I sub 1, I sub 1, I sub 1, and I sub 2, and I sub 2, it's in a clockwise direction. It's in a clockwise direction. Mark the voltage polarity across each resistor consistent with the assumed current. Remember that conventional current flow in a resistor produces positive polarity where the current enters. Okay, so just like in KCL, all of the current that is entering to the common point or to the junction, it's positive, and all of the currents going out from the point of reference or from the common point or is referred as the node or junction, then it's negative. So here, remember that conventional current flow in a resistor produces positive polarity where the current enters. So step 2, apply Kirchhoff's voltage law. So this is a symbol of this sigma is for summation. Summation of current is equal to 0 around each mesh. Trace each mesh in current. Note that there are two different currents, I sub 1 and I sub 2, flowing in opposite direction. So you will see here, it's flowing in opposite direction. I going here, and it's going down. I sub 2, it's going up. Okay. Again, trace each mesh in a current. Note that there are two different currents flowing in opposite direction. So you just have to see the arrow. Through what resistor? Through R2. Okay, through resistor 2, which is common to both meshes. Okay, again, what is common? What is the common resistor for both the meshes? It's R2, in which the currents are in opposite direction, because I sub 1 is going down and I sub 2 is going up. For this reason, two sets of polarities are shown by R2 in this figure. Trace mesh 1 in direction ABCD. So here, voltage applied, positive, it's voltage applied, it's positive because the terminal signs negative, positive. So since the direction is clockwise, so the voltage applied is positive. So what are the voltage drops? Minus I1. So here is the I1. And then the R1 minus negative sign I2, because it's the voltage drop. So this is for A, B. Take note, do not be confused. This part that we're discussing is this A, B, C, D. Okay, A, B, C, D. So here you will see I1 voltage drop, I1, R1, and then again it's negative I1, and then what is the resistor? It's R2 plus another plus I2, because it's going up, so it will become positive. So it's the drop, it's not drop. Yes, I2 is still drop, but since the direction is going up opposite with I1, so the sign here will be positive. Then R2, so equals to 0. Okay, so that is A, B, C, D. Okay, now, why did we include I2 and R2? Because that is part of the circuit. Okay, so therefore, the next thing that we're going to do now is voltage applied minus, since this 2, so since I1 and I1 is just the same, so I1, get I1, then just get R2. So it's positive R2, R1 plus R2 plus I2, and R2 is equal to 0. Then the next thing that you're going to do now is for you to be able to get now the formula for voltage applied. So transposition I1 R1 times R1 plus R2 minus I2 R2. So that is equal to VA. So question why it's minus already? Because of the transposition. So like for example here, I1 is negative, but because of the transposition, so that's why it became a positive. Okay, so same with the I2. I2 is positive here, but because of the transposition, so that's why it become negative. So note that in the first expression, I2R2 is positive, but since we go through a voltage drop from negative to positive. So it's here. Note that in the first expression, I2 and R2 is positive since we go through a voltage drop from negative to positive. So here, negative to positive, and then the I2 is here, it's going up. So it become positive. Okay. So it become positive. Okay, because it's going to the direction of the terminal negative to positive. Okay, so next, trace mesh 2 in direction A, D, E, F, A. So we're going to start now here in this point. So it's negative I2, R2 plus I1 because it's in opposite direction. So here, so I1 plus R2 minus I2. So again, negative I2 and then R3 minus the second voltage applied, which is equal to 0. So this will become positive I1, again, transposition. So I1, R2. Then here, so just like what we did a while ago, so for the mesh 1, just like what we did, so I1, so positive I1, it's here. Then R2, so R2 minus I2, so it's here. So we are going to combine here. So again, this is I1 plus R2 minus I2 and R2 plus R3 equals voltage for the second voltage applied. So it's the B. So note that, okay, so maybe you're asking why R2 and R3 is already here because we just combine I2 R2 and then this I2 and R3. So same current, so it's I2. Then since different resistors, so R2 plus R3. So note that I1 and R2 here, this is what we're referring to, is a positive voltage drop since we go through a voltage drop from negative to positive. So where is it? I1, so it's here. So I1, and then R2. So it's positive because we go through voltage drop from negative to positive. So if you are going to look at the first mesh, so I2 here, I2 and R2 is positive since we go through negative to positive. So negative to positive. So that's why it's positive. Okay, so unlike here, I1 is negative because it's from positive to negative. But here in I1, in I2, in this mesh, we're talking of this mesh. Okay, so we're talking of this mesh. So I2 and R2 is going through a voltage drop from negative to positive. So that's why it's positive. Again, we're talking, do not be confused, we're talking of the A, B, C, D. So here, so it's opposite. So we're talking here of A, D, E, F, A. So I1, and R2, I1 and R2 is going through a going to a voltage drop from, you will see here, it's negative to positive. So that's why it's positive, okay? Because the direction is going from A, D, E, F. So opposite from mesh 1, because we go through here, okay? From A, B, the direction is A, B, C, D. Okay. So do not be confused. So that's why here the I2 is I2 and R, because the direction is going up. Whereas here I1, the direction is going down and it's from negative to positive. So that's why it's positive. So find I1 and I2 by solving equation 1 and 2 simultaneously. So you're now going to look for the current 1 and the current 2 by using the two equations. For mesh 1, so for voltage applied, it's this, I1 times R1 plus R2 minus I2 and R2. So in VB, so it's I1 R2 minus I2 times R2 plus R3. So step 4, when mesh currents are known, find all the resistor voltage drops by using Ohm's law. Okay, so this time you will be using the Ohm's law now in finding for the resistor. So here, after step 4, after finding for the resistor, when all of the currents are already known, step 5 is check the solution of mesh currents by tracing mesh A, B, C, D, E, F, A. So it's this, A, B, C, D, E, F, A. So all of the elements that is, all of the components that is part of this mesh current. So VA, voltage applied, minus I1 R1 minus I2 R3 minus VB is equal to 0. So how is this? So let's see. So why the formula is like this? Because we will be looking now for the total current. That's for the whole current. It's A, B, C, D, E, F, A. So that's for the whole current. It's for the whole loop. So that's why it's called mesh. Because it's complicated because it's not just a one current backgrounds. So given VA, or the voltage applied, is 48 volts. The second voltage is 10 volts. So for R1, it's 4 ohms. R2 is 3 ohms. R3 is 2 ohms. Find all mesh currents and voltage drops in the circuit. So step 1, choose 2 loops or meshes shown. Show mesh current in the clockwise direction. Show polarity marks across each resistor. So this is mesh 1, this is mesh 2. Mesh 1 is A, B, C, D, A. Mesh 2 is A, D, E, F, A. So step 2, apply the summation of the currents that is equal to 0 in mesh 1 and mesh 2, and trace the mesh in the direction of mesh current. So mesh 1, A, B, C, D, A, 58 minus, so negative sign R1 times current 1. So it's negative because from here, R1 is here, and I1 is here. So this is the direction, so that's why it's negative voltage drop. Minus, so negative again for R2, because same direction, I1, because the I1 direction. So this time, it's positive because of the direction of the current 2. So here is current 2. So equals to 0. So negative 4 minus 3, it's 7, negative 7 actually, it's negative 7, plus 3, I2 is equal to 0. So transposing 58 to have the equation 1. So by transposing, so that's why the negative 7 becomes positive 7. The negative 3I2, the positive 3I2 becomes negative. So next is mesh 2. A, D, E, F, A. So here, R3, it's not R3, so it's R1. Where's R1 here in ADF? In ADFA, so this is AD. So ADFA, R2. So this is R2. So R2 and I1. So this, it's positive because it's I1, so it's opposite direction with the second source. So with the second source, it's opposite direction So this is the I1. So this is the I1. So that's why it's positive. Again, here is the I1. And it's the second source. It's going in. Okay, so here I2, it's negative. So I2, it's negative. The sign is negative. Here's I2, it's negative because it's clockwise. The direction is clockwise. So it's negative. So same here with I2. So again, it's negative because it's clockwise. So it's negative because it's clockwise. So the only positive here is the I1 because the direction is opposite. So if you will see the mesh 1, you will see in mesh 1, the one that is in opposite direction is I2. So that's why I2 is positive. So here, the one that is in opposite direction is I1. So that's why it's positive. Okay. So correct me if I'm wrong. You will observe now, if this in mesh 1, the first mesh, when transposing the sign of the given element here is being changed. But here in every second mesh, correct me if I'm wrong, when you transpose now, then the sign will not change. Like for example here, 3, it's also positive. For here, actually it's negative 3 minus 2 is negative 5. Okay, so negative 3 minus 2 is negative 5. So still, even if the 10 is being transposed, for us to be able to get the equation 2, still the signs are still the same. So unlike in mesh 1, transposing 58 will change the sign. Transposing the voltage applier will change the sign given. Whereas in mesh 2, there will be no changes for the sign even if VB has been transposed. Okay. So we're able to get now equation 1 and equation 2. So note that mesh currents I1 and I2 flow through the common resistor R2. So here is R2. So both I1 and I2 flows through the common resistor R2. So step 3, we are now going to find I1 and I2 by solving equation 1 and 2 simultaneously. So again, the equation 1 is 7 I1 minus 3 I2 is equal to 58. Whereas for ADEPA mesh 2, 3 I1 minus 5 I2 is equal to 10. So for us to be able to get I1, first to be able to find I1, we are going to multiply equation 1 by 5. Why 5? Because 5, this is the 5 here. Okay, we refer this 5 here. So multiply equation 2, this one, equation 2, by 3. Okay, this is where we're going to get 3. So getting equations 1a and 2a. So 5 times 7, 35. 5 times 3, 15. 5 times 58 is 290. Then for the second equation, multiply it by 3. So 3 times 3, 9. 3 times 5, 15. 3 times 10 is 30. So it's now time to add. It's now time to, yes, to subtract for us to be able to get I1. So 290 minus 30 is 260. Then cancel 15, 15. So we're going to cancel this. So 26I1 so the 260. So let us now divide 260 by 26 for us to be able to get I1. So 260 divided by 26. So that's why we have 10. Okay, so let's now have, okay, for us to be able to get the I2, so I1 is 10 already. So for us to be able to get I2, let's do substitution. So 7I1 minus 3I2 is equal to 58. So we'll be using the first equation now since we're done using the given for equation 2. So let us now substitute 7 times 10, because that's the I1, minus 3I2 is equal to 58. So 7 times 10, so negative 3I2 is equal to 58 minus 70. So 58 minus 70, or you just have to change 70 minus 58, since there's no negative current. 70 minus 58 over 3, cancel. So that's why we have I2 now. We'll be using the 3. So 70 minus 58 is 12 over 3. So we have 4 amperes. So the current through branch DA, the current here now is 6 amperes. Why? Because I1 DA is I1 minus I2, so I'll do 10 minus 4, so it's 6. So in this case, the assumed mesh current direction was correct because the current values are positive. If the current value were negative, the true direction would be opposite to the assumed direction of the current. So that's it. So step 4, for us to be able to get now the voltage drops. So V1, here's V1. So it's I1 times R1. So 10 times 4, it's 40 volts. For V2, it's I1 times R2. It's I1 times R2. But since there are 2 current passing here, so it will be I1 minus I2. So it's 6. 6
Okay,
times
so
3 is
note
18
voltages. Another
Because again, there
method
are
for
2
solving a
currents
circuit
passing
with
here
mesh currents
in
uses the
V2.
voltage drops to to specify the
So
currents at a
V3,
node. Then, node equations of currents are written
V3
to satisfy Kirchhoff's
is
current
here.
law.
So
By
I2
solving the
and
node
R3.
equations, we can
So
calculate the
I2
unknown
is
node
4 and R3
voltages.
is 2.
A node is a common
So to
connection for
check
2 or more
if
components. A principal node has 3 or more
it's
connections.
correct,
To each
so check
node
mesh
in a
current solution by
circuit,
first
letter or
loop
number is assigned.
A,
B,
C,
G, and
D,
N
E, F, A, and apply
are nodes, and
KVL.
G and
We
N
often go into
are principal
KVL.
nodes or
So
junctions.
it's
You will see the
V
figure
voltage
later.
applied
A node voltage is the
minus
voltage of a
the
given
total
node with
voltage
respect to one
drop. So to
particular
see
node called the
we have
reference node.
58,
Select node 6 connected to
58
chassis ground
minus
as the reference
40,
node. Then the voltage AG is the
40
voltage between nodes A and
V1.
G.
So here's
Voltage
V1.
BG is the voltage between
So
nodes
V1
B and G, and
minus
V and G
V3. So
is the voltage between nodes N and G.
minus VB.
Since the node voltage
So
is always
so maybe
determined
you are
with
asking why
respect
we
to
did not
specified
include
reference
V2
node,
because
the
what we
notations
are
V applied
checking now
for
is the whole
VAG,
circuit.
VB
So 58
for
minus
VBG,
55. So
and
check.
VN for VNG are used. So you will see here.
Okay.
So node voltages.
So if you have questions,
Okay,
feel
so
free
it's
to
here.
write in the comment section.
So you will see again. Okay, for you to be able to relate, let's check this one. Okay, so again,
Okay, so node voltages.
so here in
Another
figure
method for
9,
solving a circuit with mesh currents uses the voltage
to each
drops
node in a
to
circuit, a
specify the
letter or
currents at the
number
node.
is
Then
assigned.
node equations of currents are written
So
to
we have
satisfy
here
Kirchhoff's current law.
A,
By solving the node equations, we can
B,
calculate the unknown node voltages. A
G,
node is a common connection
N
for 2 or more
are
components. A
nodes,
principal node has 3
and
or more
G and
connections.
N
To
are
each
the
node in a
principal
circuit, letter or number is
nodes.
assigned.
Again, the common
A, B,
nodes,
G, and N are nodes,
the
and G
nodes
and
here
N
are
are
the
principal
following:
nodes or junctions. We'll see the
B,
figure later.
G, and N.
A node
But the
voltage is a
principal
voltage
node
of a
is
given node
G
with
and
respect to
N.
one particular node called the reference
Okay, nodes or
node.
junctions.
Select node 6
Again,
connected to chassis ground is the
a
reference
node
node.
voltage is the voltage
Then the
of a given
voltage AG
node
is the voltage
with
between
respect to one
nodes A
particular
and
node
G.
called the reference node.
Voltage
So select
VG is the
node
voltage
G,
between nodes
G
B and
connected
G,
to
and B
chassis
and
ground as
G
the
is
reference
the
node.
voltage between nodes N
Then
and G. Since the node voltage is always determined
A,
with respect to specified
voltage
reference node,
AG
the notations be applied for
is the voltage between
VAG,
nodes A
VB for
and
VBG,
G.
and VN for
A and
VNG are
G.
used. So you will see here.
Okay.
So node voltages.
Okay,
Okay,
then
so
V,
it's here.
VBG.
So you will see
VBG is the voltage
again.
between nodes B and G.
Okay.
And
For the
voltage
relay, let's check
NG
this one.
is the voltage between nodes N and G. Since the node voltage is
Okay,
always determined
so
with respect to the
again,
specified reference node, the notations
so
VA
here in figure
for
9,
VAG,
to
VB
each node in a circuit,
for
a letter or
V
number is
for
assigned.
VBG,
So we have
and
here
VN.
A,
VN for
B,
VNG are used.
G,
Okay?
and N.
So
are
with the
nodes.
exemption of the reference node, the
And
equations
G
using
and N
KCL
are
can
the
be written at each principal
nodes.
node.
Again,
So where's
the
the principal
common
node?
nodes,
It's here, N and G.
the nodes here
Thus, the
are the
required number of
following: J,
equations is one less than the
B,
number of principal nodes. Since
G,
the
and
circuit
N.
shown in the
But
figure
the
has two
principal
principal
node
nodes,
is
N and G,
G
only
and
one
N.
equation need to be written at node N
Okay, nodes or
to find
junctions.
all voltage drops and
Again,
currents in the circuit.
a node voltage is the voltage
So
of
node
the node
voltages
with respect to
assume
one
that
particular
branch
node
currents
or the
I1
reference node. So select
and
node
I2
G, this is G,
enter
connected
node
to
N.
chassis ground as the reference node.
Okay,
Then voltage
so
A,
in key
voltage
you will
AG
recall the
is the voltage
KVL,
between nodes
I
A
mean the
and
KCL.
G.
So the KCL
A
states that
and
the sum of
G.
the currents entering a junction or a node
Okay.
is equal to the sum of the currents leaving the
Okay,
junction.
then B,
Okay,
VBG.
so if we consider
VBG is the voltage between
currents
nodes
flowing to a
B,
junction are positive, and those
nodes
currents flowing
B
away from
and
the same
G.
junctions are
And
negative.
voltage
So
NG is the voltage between nodes N and G.
and so here
Since the node
I1 and
voltage is always
I2 is
in
entering
relation
node
to its
N,
reference node, the
and
notation is
I3 and
for
I3
VAG, VB
I3 is leaving N,
for V,
leaves the node.
for VB,
So then selection with direction of the current
G,
is arbitrary from
and
KCL.
VN,
Summation I is
VN
equal to
for
0.
V
So
and
here
G
it's I1
are used. Okay.
plus I2 minus
So with the
I3
exemption of
is
the
I3 is
reference
the one
node, the
leaving.
equations using
So equals to
KCL can
0.
be written
So
as
I3 is
principal
equal to I1 plus
node.
I2.
So where's the
So that's the
principal node?
equation.
It's here, N
So
and
I3
G.
is equal to
Thus, the required
I3
number
is
of
equal to
equations is
Vn
one less than the number of principal nodes,
Vn
since the circuit shown in the
over,
figure has two principal nodes
so
N and G.
Vn
Only one equation needs to be
over
written at node N
R2,
to find all
it's
voltage drops
here,
and currents
R2.
in the circuit.
For us to be able to get I3,
So node
by Ohm's
voltages,
law,
assume that branch
Vn,
currents I1
by Ohm's
and
law, you know that
I2 enter node N.
it's the VIR, V times I times R. So therefore, we're going to look now for the
So
current. So it's V over
in
R.
T,
So
you
the
will
Vn,
recall
so it's here based
the
on the given
KVL,
circuit.
I
So
mean the
Vn over
KCL.
R2.
So the
Yes, R2
KCL
is the
states that the
one
sum of the currents entering a
in
junction
which the
or a
current
node
I3 passes
is equal to the sum of
through.
the currents
So for I1,
leaving the junction.
it's VA. Here's
Okay.
I1. VA minus
So if you consider
VN. So
currents
because we
flowing
have
to
here
a
E
junction are
and N,
positive, and
so
those currents flowing
VA
away from the same
minus
junctions
VN over
are
R1.
negative.
Because R1 is the one here.
So
So that is equation 1A. I mean 1B.
and so here I1 and
For
I2 is entering
I1,
node N,
another for I1,
and I3
we have
and
VB,
I3
VB
I3 is
minus
leaving N,
VN.
leaves the node.
So over R3.
So then selection with direction of the current is
So R3. So here is
KCL.
R3.
Summation I is equal to 0. So here it's I1 plus I2
So
minus
substitute these
I3, because
expressions
I3
in
is
equations
one
1.
leaving. So equals to 0. So I3
So
is equal
Vn
to I1 plus
over
I2.
R2.
So that's the equation. So,
So
I3 is
Vn
equal to
over
I3
R2.
is equal to Vn
So
over
here,
So Vn over
So it's I2.
R2.
So to VA minus
This is here.
VN.
R2.
So here is
for us to be
VN.
able to get I3,
So VA minus
by Ohm's
VN
law,
over R1
Vn,
plus
by Ohm's law, we know that
VB minus VN over
so the
R2.
VIR, V times I times R to therefore
Okay.
we're going to look now for the current, so it's V over
VN.
R.
So because
the
that is the
Vn, so
equation
it's
for
here, this is the given
this one, it's I2 by the way.
circuit,
It's
so
I2.
Vn over R2, this R is the
Okay,
one.
so here, just substitute the expressions, the equation
So for
1.
I1,
So here is now equation 2.
it's VA, here's I1,
So VA,
VA
VB,
minus
R1, R2, and R3
VN.
are known. So
because
VN
we
can
have
be
here A and
calculated from
N,
equation
so
2.
VA
Then all
minus
voltage
VN
drops and
over
currents in the circuit can be
R1.
determined.
R1 is the one here.
So example
that
2,
is equation 1A. I mean
the circuit of
1B.
figure solved by the method of branch
For
current is revealed in
I1,
figure 10,
another
solved
for
by node
I1,
voltage analysis. Step 1,
we have VB,
assume the direction of current shown in figure 10.
VB
Mark
minus
nodes A, B,
VN.
N, and mark the voltage
So over R
polarity across each resistor
R3.
consistent with
Here's
assumed direction
I3.
current. So step 2, apply KCL at principal node and solve for Vn.
So
I3
substitute this expression
is
in
equal
equations
to
1.
I1 plus I2.
So Vn over R2.
So through the given
Vn
equation,
over R2.
so R2 is 3.
So here,
we already know what is R3. So it's 3.
so it's
I mean
I2.
R2. So it's 3.
So the VA
So equals
minus
to
VN.
VA, it's 50.
So here
Minus
is
VN,
VN.
because VN is still
So
unknown.
VA minus VN
Over 4 plus
R1
10, because VB is already
plus
given. Minus VN,
VB
again, it's still unknown.
minus
Over
VN
2 because
over
of R3.
R2.
It's already here, R3.
Okay.
So clear fractions by
VN.
multiplying each term.
So because that is the
by
equation
12.
for this
So
one,
let
is
us now
I2 by the way.
multiply
It's I2.
each term by 12.
Okay, so here, just substitute the expressions.
Okay, so
the equation 1. So
for
here is now
Vn
equation 2. So
is equal
VA,
to,
VB, R1, R2, and R3 are known. So Vn
okay,
can be calculated from equation 2. Then all voltage
here,
and currents in the circuit can be determined.
clear fractions by multiplying each term
So
by
example
12
2,
by 12. Because
the
we are
circuit
going
of
to get
figures
now
solved by
in
the
this
method of
equation, we're
branch
now going
current
to get
solved by
the
node
term,
voltage
the
analysis.
LCD.
Step 1,
So
assume the
since
direction of current shown
8
in
is
figure
not
10.
visible by 3,
Mark nodes A, B, N, and mark the voltage
so let's just use 3
polarity
times 4,
across each
which is
resistor
visible to all
consistent
of
with
the
assumed
3
direction
numbers.
current.
So
So step 2, apply
it's
KCL at principal node and solve
by
for
multiplying by each term
So
to each
I3
term, so we
is
will
equal
get
to I1 plus
12,
I2.
12 Vn over 3.
So through the given equation,
12 Vn over 3
so R2 is
equal to
3.
12
So
times 58, it's
we already know what is
696
R3. So it's 3.
times
And in
another
R2,
times 12 Vn,
so it's
so minus
3. So
12
equals to
Vn
VA, it's 58.
plus
Minus
10 times
Vn because
12 is
Vn is still
120
unknown.
minus 12 V.
Over 4 plus 10 because VB
Okay,
is
so
already
here
given. Minus Vn,
we will
again,
get,
it's still unknown.
we have here
over
12.
2 because
So
of
12
R3.
divided by 3
It's
is
already
4.
here, R3.
Vn.
So clear
here,
fractions by multiplying each term
696
by 12.
divided by 4.
So let
So
us
it's
now multiply each
174.
term by 12.
So it's 174. Then 12 here divided by 4. So it's Vn.
4
So
Vn
it's 3 plus
is equal to
plus 120
okay,
divided by 2. So it's 60.
Okay, so here
And 12
clear
divided by
fractions
2,
by
it's
multiplying
6.
each term by 12. Why
Okay,
12?
so next, what
Because
we're going
we
to
are
do
going
now,
to get now in this equation,
for us to be able to get the Vn,
the term,
is
the LCD. So since
174
8
plus
is not
60,
divisible
so
by
that is
3,
234.
so
why
let's just
13?
use 3 times
Because
4,
you add
which
4.
is divisible to all
So
the three
since there will
numbers.
be, you're going to
So
transpose
it's
negative this 3 and then
by
6, so that's
multiplying
why it
by
becomes
each
positive
term,
here. So
so
4
we
plus
will get
3 plus 6. So we will have 13
12
Vn.
12
So
Vn
it's equal to 34
over
divided by
10.
13. So we will get 18 volts.
12 Vn
So that's
over
why
10
Vn is equal to, here it's
is equal
18
to 12
volts.
times 58 is 696
So first step,
times
3,
another
find all
times
voltages,
12
drops,
Vn,
and
so minus
currents.
12 Vn
So V1, again
plus
V1,
10 times 12 is
V1,
120 minus 12 Vn.
where's the V1 here? So
Okay, so
V1 is
here
equal to
we will get,
VA
we have
minus
here
VN.
12. So
So
12
58 minus
divided by
18 is
3 is
40
4
volts. So V2,
Vn.
it's
So
VN
here
minus, so it's
696
VN.
divided
So
by
it's 18
4,
volts.
so it's
So for
174.
V3, it's
So it's
VB,
174.
it's a VB,
Then 12 here
and
divided by
VN. So
4.
it's 10 minus
So
18.
it's
So it's negative 80
Vn.
volts.
So it's
The negative
20
value for V3 means
plus
I2 is flowing opposite to the
120
assumed direction.
divided by
And the
2.
polarity
So
of
it's 60.
V3 is the reverse of the sign
And
shown
12 divided
across
by 2,
R3.
it's 6. Okay, so
So
next,
I1 is
what we're going to
V1
do
over
now,
R1 equals 40 over 4 is
for
10
us to be able to get
amperes.
the Vn,
I2 is V3 over R3. It's negative
is
8 over, so it's negative 4 ampere. That is
174
because of the
plus
direction, so that's why it's
60.
negative.
So that is
So where is
234.
I2 here?
So why 13?
I2 it's here.
Because you add 4. So since
So
there
it's
will be, you're going
negative.
to transpose
So
negative
I3 is
this
I1 plus
3 and
I2 is
then
equal
6. So
to
that's why it
10
becomes positive
minus
here.
4
So
because it's
4
negative.
plus
So
3 plus 6.
I3
So we
now
will have 13
is
Vn.
6
Vn.
amperes.
So it's equal to
Where's
34
I3?
divided by
I3 is
13.
here.
So we will get 18
So I3
volts.
is I1.
So that's why Vn is equal to, here it's
I1 plus I2.
18 volts.
So
So for
given
step
the
3, find all voltages,
amperes,
drops, and
so
currents. So
I3
V1,
is equal to 6
again
amperes.
V1, there's V1, there's the V1 here. So V1 is equal to VA minus VN. So 58 minus 18 is 40
I2,
volts. So
V3,
V2, it's VN
V3, where's V3?
minus, so it's
I2 it's
VN.
V3
So it's 18 volts.
over R3
So for V3,
over R3,
it's VB.
so negative 8 divided
It's a
by 2,
VB.
it's negative 4.
and Vn. So it's 10
So
minus
same.
18.
It's negative
So it's
4.
negative 20 volts.
So
The
check.
negative value for V3 means I2 is flowing opposite to the assumed
I1.
direction, and the polarity of
I3 is
V3 is the
I1
reverse
plus
of the sign
I2.
shown
So 10
across
minus 4
our
is equal to
tree.
6 amperes. So I3, check. 6
So I1 is
amperes.
V1 over R1, plus 40 over 4 is 10 amperes.
I3,
I2 is V3 over R3, it's negative 8 over
this is
so
not
it's negative 4
actually
ampere.
I3.
That is because of the direction, so that's why it's
I,
negative. So
where's
where's
V2?
I2 here?
V2
I2 it's
and
here.
R2. So it's I3,
So
I3.
it's negative.
So V2 over R2
So I3 is I1 plus I2
is equal to
10
V2
minus
is
4 because
18
it's negative. So
over
I3
3
now
for R2. So it's
is
equal to
6
6 amperes.
amperes.
So check.
First I3,
So just the same.
is here.
So
So
18
I3 is
divided by
I1,
3. So check. So all calculated values
I1
agree
plus
with those of
I2.
example 1.
So given the amperes, so I3 is equal to 6 amperes. I2, V3, where's V2? I2 is V3 over R3, so negative 8 divided by 2, it's negative 4. So same, it's negative 4. So check. I3 is I1. I3 is I1 plus I2. So 10 minus 4 is equal to 6 amperes. So I3, check. 6 amperes. I3, so this is not actually I3. So first V2, and R2, so it's I3. So V2 over R2 is equal to V2 is 18 over 3 for R2, so it's equal to 6 amperes. So check. So just the same. So 18 divided by 3, so check. So all calculated values agree with those of example 1.